Greetings and welcome to Chapter 5, Continuous Random Variables. We're going to go over Lesson 5.1, Continuous Probability Functions. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. One of the major differences when talking about continuous probability than what we've been studying, which was discrete probability, is the numbers that were allowed. In discrete probability, we were working with numbers that were countable, 1, 2, 3, 4, 5. With continuous probability, it's going to be everything in between as well. So the graph of a continuous probability distribution function is a curve. It may not look very curvy depending on what type of distribution we're working with, but it is a quote-unquote curve. That curve we're going to call f of x, and that's our probability density function. The area of the curve is the cumulative distribution function. It's the sum of all of our probabilities. And of course, the sum of all of our probabilities better add up to 1. Now, when we're talking about finding probabilities, we could do something like P of C is less than X is less than D. That means we're looking for the probability between the value C and D. For example, if I said I wanted the probability that X lies between 4 and 6, then the probability that 4 is less than X is less than 6. If I'm talking about a specific value, the probability of X equals a value, let's say 2, that probability is going to equal 0. And I'll explain that in just a second, why that is. Because the probability of X equaling a specific number is 0, that means the probability of C is less than X is less than D is exactly the same as the probability of C is less than or equal to X is less than or equal to D. Having that equal doesn't change a thing because that equal part is going to add up to 0. Now let me roll back and talk about that probability of X equaling a value and why that probability does equal 0. If it is the area under that curve, then that area is generally at least estimated with length times width. So pretend it's a very tall, skinny rectangle, and the area of a rectangle is length times width. The problem with our X being only solely the width of one value is that really isn't a width. The width has to be the difference of something. It has to be the fatness of, let's say, 3 and 4. Well, that's the width of 1, or 3 and 5. That's the width of 2. To get from 3 to 5 is a width of 2. To get from 3 to 4, the width is 1. To get from 3 to 3, the width is 0. And 0 times anything is 0. And therefore, the probability of X actually equaling that specific value is always going to be 0. Let's look at a continuous probability function that's fairly straightforward. I'm going to give you some information. We're going to consider this function is f of x equals 1/20th. That's our function. And these values are good from 0 to 20. So x can be anywhere from 0 to 20. If we graph this, our boundary is 20, our boundary is 0, and think of it as your y value, your f of x value is always 1/20th. That shape is a rectangle. Everything underneath that line of 1/20th, inside that rectangle, our probabilities. And if you add all of them up, all of those probabilities must equal to 1. So let's think about this. The area of a rectangle is length times width. We know our length, we'll just say that's the base of our rectangle, our length, and that goes from 0 to 20. And our height of the rectangle is 1/20th. So length is 20, width is 1/20th. 20 times 1/20th is 1. So our area definitely in our rectangle adds up to 1 or is calculated to 1. Suppose we now want to find the probability that x is in between 4 and 15. So we want to find the area. Our function is still the same, 1/20th, but we only want the area between 4 and 15. Let's find the probability. Working out our length, our base of our rectangle, that's going to be our high value, 15, minus our low value of 4, times our height, in other words, our width. 15 minus 4 is 11. 11 times 1/20th is 11/20th. In other words, our probability that x is between 4 and 15 is 0.55. Fairly straightforward calculation. I'm always looking for the area under the curve. The area under the curve in this situation is a rectangle, so I'm always going to find the length times the width, or we can say the base times the height. The height didn't change from the previous scenario, but the base did. So we did have to calculate our base. Here we have a third scenario. Suppose we want to find the area for our f of x equaling our 1/20th and our x-axis where it's 3.8 to 13.3. None of the math has changed, just the numbers. So our area is still a rectangle. We need to figure out how much is our base of our rectangle, how much is our height of our rectangle, multiply the two of them together to get our probability, our area under our curve, the purple area. This time, our high boundary is 13.3 minus our low boundary of 3.8. That's going to be the base of our rectangle, times our height, which is still 1/20th. We get 9.5 times 1/20th. Throw that into a calculator. You get the probability that x is between 3.8 and 13.3 is 0.4750. One last situation for right now. Let's suppose we want to find the area between our f of x, our 1/20th, and the x-axis where x equals 7. Now you can think of this, if x equals 7, then our lower bound is 7 and our upper bound is 7. So 7 is less than x is less than 7. We can say 7 minus 7 is 0. 0 times anything is 0. So the probability that x is exactly 7 is 0. And in fact, if x is any number, if it equals any number, your answer is always going to be 0 because the area in a line has no width. I know we can draw it with width, but technically it has no width. You don't have a high, you don't have a low, so you have no width to it and or length to it, depending on how you're looking at it. And therefore 0 times anything is always going to be 0. You've reached the end of this lesson.